Hey everyone, this is Dr. Walker. This is going to be a very short video giving us a brief overview of how we're going to use Gauss's law to various charge distributions. The bulk of the work is going to be done in the guided examples that follow, but in this video I just want to go over a couple of very important points for how we're going to do these types of problems. So the two things to keep in mind when using Gauss's law is that the electric field has to be constant over the portion of that Gaussian surface that we choose for that charge distribution. And the second thing is that E and dA have to be parallel. This is going to allow us to use Gauss's law. If we write down Gauss's law, the electric flux is equal to the surface integral of E dot dA, which is equal to the charge enclosed over epsilon naught. Then, first of all, if we have a certain charge distribution, let's say a sphere just for now, right? And then we pick a Gaussian surface to also be symmetrical, to be spherical, then the electric field is going to be constant everywhere on that surface. Everywhere on that surface, the electric field will have the same value. So if E is constant, it can come out of the integral. And the other thing is that if you take advantage of symmetry, then E and dA are going to be parallel. So you can see in this case, E is parallel to dA. dA is the vector that is perpendicular to our surface here. And that allows the dot product to cancel out so that we just get EdA, which when I already took out E, I already assumed that the dot product was canceling out. I was a little bit ahead of us. But the integral of dA is just E times A. So this is what's really important to remember when we're using Gauss's law. If we take advantage of symmetry, then we're going to end up with this equation, and then it's going to be relatively easy to solve for E because we just divide this expression by area. So in order for us to simplify Gauss's law so that we can use it like this, the problem has to have a certain type of symmetry. And the three types of symmetry that make it really easy to use Gauss's law are going to be spherical symmetry, cylindrical symmetry, and planar symmetry. So if a charge distribution is spherical, or it can be concentric spheres, then we know we can have a Gaussian surface that would be spherical. If we have a charge distribution that has cylindrical symmetry, it can be a line of charge, it can be a cylinder, it can be concentric cylinders, and we'll figure out what kind of Gaussian surface can take advantage of that type of symmetry. Likewise, for planar symmetry, we can have a plane of charge, or we can have two planes of charge, and we'll be able to find a Gaussian surface that takes advantage of that symmetry such that the field is constant over that surface and E and dA are parallel, and then we'll be able to solve for the electric field due to these charge distributions.